Hey team, welcome. Let's just jump right in, shall we? Today, I want us to put on our pragmatic, lead engineer hats for this explainer. We are going to take a completely no-nonsense look at what it actually takes to ship LLM features safely to production. We're bypassing all that theoretical fluff and focusing purely on the stuff that actually prevents a 2 a.m. pager alert when your model inevitably starts behaving unpredictably. We're talking about the pragmatic guardrail stack.
Okay, let's dive straight into this architecture review. We'll be explicitly triaging what we actually need to build today versus what can wait until later.
So let's kick things off with a little guardrail reality check.
Look, we've all sat through those theoretical conference talks on production LLMs, right? You know the ones. They always present this standard list of 5 security layers. You've got an input filter to stop prompt injection, output schema validation to ensure structured data, a hallucination boundary to double-check facts, a tool and action policy to control the agent, and, of course, human-in-the-loop oversight. And the heavy implication is always the same. If you don't build all 5 of these things right this second, all at once, you're going to be deeply, deeply sorry.
Well, here is the crucial point. That implication, it's just wrong. Honestly, out of those 5 layers, exactly 2, just 2, carry the actual weight on day 1. The other 3 layers are, frankly, mostly security theater for the vast majority of features you'll ship. Don't get me wrong, they are incredibly useful eventually, but until a specific trigger fires, they just aren't the thing standing between your new feature and a massive critical incident.
Because at the end of the day, a guardrail earns its keep by answering one very simple question. What breaks if I don't have it? We're really protecting against 2 primary failure modes here. First, the model returns completely unusable text, like malformed JSON, crashing your pipeline with a 500 error. Second, the model performs an unintended action, like firing off the wrong email to an important client, which causes actual asymmetric harm. The cleanup for the first one is just an annoying error log, but the cleanup for the second, that's manual, it's expensive, and honestly, it's pretty embarrassing.
Which brings us to our absolute first, non-negotiable, load-bearing layer, output schema validation. This is what turns an interesting demo into a stable, production-ready feature.
Without this layer, your LLM call just returns a raw string, and your code basically has to cross its fingers. With it, every successful call guarantees a typed object. To get there, you need these 4 code-level steps. Step 1. Define a typed schema that describes the exact structure your downstream code expects. Step 2. Nudge the model to actually comply, using JSON mode, a tool call schema, whatever works. Step 3. Use a validate parsers to strictly check the response against your schema. And Step 4. Build a robust repair and retry loop. And crucially, you have to enforce these parser checks right in your standard CI/CD pipeline. If a mock LLM string fails your type schema tests, your build should immediately break, no exceptions.
Now, let's zoom in on that repair loop, specifically using a fallback library like JSON repair. I know it's incredibly unglamorous, but it is absolutely vital. Language models are notorious for returning malformed JSON syntax. We're talking trailing commas, using single quotes instead of double quotes, or sneaking a stray new-line character right inside a string. Using a fallback library to fix this 90% case of trivial formatting errors before you completely give up is worth significantly more than trying to engineer some magically smarter prompt. It just stops your pipeline from crashing on basic syntax mistakes.
But here's the catch. Repair loops only handle syntax. They don't handle semantics. If the model returns the word hi instead of the integer 85 that your schema demanded, no parser in the world is going to fix that. For semantic errors, you literally have to hand the validation error back to the model and ask it to try again. And the magic number here is exactly 2. 2 retries is the absolute sweet spot in practice. If you find yourself doing 3 retries, you are just paying for variance. If it's still failing after 2 retries, you need to realize the prompt is the actual problem, not the model.
And when it does inevitably fail, the error type matters immensely. If the LLM genuinely cannot produce a valid result, maybe the input was just way too thin or a web page didn't load properly, you want a typed error, something like an insufficient job data error, bubbling up cleanly. You absolutely do not want a generic, deep parser validation error. Custom-typed errors make your downstream code so much easier to reason about, which means the rest of your system can finally stop defensively checking the LLM's output.
All right, let's move on to our other massive day 1 priority, tool policy. Okay, I'm putting my security reviewer hat firmly on my head right now, because the exact moment we give an LLM tools, the game completely changes. I want to be perfectly clear with a strict zero-trust tone here. There is no "we'll just be careful" version of this. Giving an agent tools immediately escalates the blast radius from an annoying 500 internal server error to asymmetric harm. If an agent can write to a production database, file a ticket, or charge a credit card, a simple bug means you're going to be writing a lot of apology emails to your customers.
Because of that, a real tool policy has 4 non-negotiable sublayers. First, you need a hard-coded allow list per agent. If an agent only ever needs to read a calendar, it should absolutely not have the send_email tool registered. Second, strictly scoped credentials. And you need to test this. Run unit tests that assert the agent's token receives a literal 403 forbidden error when it attempts unrelated API calls. A massive red flag here is an agent holding admin or write-all scopes for a task that strictly requires read-only access. Third, you need human-in-the-loop drafts for anything that changes external state. And finally, idempotency keys for retries, so a random network timeout doesn't result in the agent executing the exact same action twice.
And this brilliantly illustrates the absolute safest way to implement those rules, the drafts table pattern. In this architecture, the LLM doesn't actually send or execute anything. It drafts. It writes a row to a database. That's it. It never even holds the credentials to execute the final action. A completely separate, highly audited, non-LLM code path handles the actual execution, and it only triggers after a human changes that row's status to approve.
Now, when you are ready to test these tools out in the real world, you must implement a dry run flag as a first-class mode. This is absolutely critical. It allows you to watch the agent operate safely, right in your production logs without actually authorizing any actions. You can just read the dry run logs for a week, audit how well you've scraped those minimal credentials, gain some real confidence, and then, and only then, flip the switch for the safe tools. Honestly, you can keep the more dangerous ones on dry run forever if you need to.
Shifting back into our pragmatic lead engineer persona now, we've mapped out when we actually need to build the rest of this stuff.
Okay, so we've secured our schema and our tools, but what about the other 3 layers? Well, we build them when specific external conditions or triggers actually fire. If your prompt incorporates untrusted external content or you're running a multi-tenant product, boom, that's your trigger to build an input filter for prompt injection defense. If you handle regulated data like HIPAA or GDPR, or if your logs are accessible by third parties, that mandates an output PII filter. If your product provides medical or legal advice, or operates a RAG system where the implicit contract is answers only come from these docs, well, that's your trigger to build a strict hallucination boundary. Until those specific triggers fire, you just don't need them.
So, let's bring it all together with a concrete triage checklist. Let's move to and see how this builds a strict order of operations for your roadmap today. Step 1 is output schema validation on day 1. You prioritize parser stability and get those repair and retry loops humming in your CI/CD. Step 2 is your tool and action policy, which you implement the exact moment the agent does anything other than generate text. Prioritize that drafts table pattern and action safety. And step 3, those are your conditional layers, built only when those specific external risks actually emerge. I'll leave you with this final, slightly provocative question to ask your team tomorrow morning at stand-up. Are you building theater or are you building actual guardrails? Treating all 5 layers as equally urgent right out of the gate is exactly how engineering teams waste a whole quarter on unnecessary prompt injection defenses, only to ship a feature whose actual catastrophic problem is that the JSON parser crashes every single Tuesday. Focus on what breaks, build the load-bearing layers first, and let's ship safely.
If you found this helpful, hit subscribe and the bell so you never miss a video.